Dr. Eldering is working to leverage her considerable expertise with satellite missions to connect satellite measurements of greenhouse gases with the greenhouse gas measurement program at NIST. And it's in that context that this week she's given us this series of lectures focused on greenhouse gas measurements from space, getting to precise and useful observations. So we began the week with the discussion of the limitations of the previous network for observing CO2 and the scientific motivation for measuring CO2 from space. And then we learned about the challenges of building the NASA orbiting carbon observatories, and then talked about some of the exciting future missions that will measure greenhouse gases from space. And then yesterday, we learned a bit about ground-based measurements that will complement the satellite measurements and exciting new laboratory techniques that might provide spectroscopic information to help us improve the satellite measurements. So today we're going to hear about a key motivation behind the considerable investments that space agencies around the world have made in developing these missions, and that is the societal or policy applications. And so the title today will be on atmospheric greenhouse gas measurements in the context of international policy, putting scientific observations to use. And so please join me in welcoming Dr. Eldering for this final lecture in the series.
All right, thank you, Dylan. Wow, great to see everybody here, and thank you for not abandoning me yet in the end of this long week. Great to see all the faces in the audience, and we probably have a few folks online as well. Let's see, let me do that. How's that sounding okay in the back? Good. All right, thanks for that intro, Dylan. It sounds like Dylan was paying attention this week, so that's great to see. He actually knows what the conversation was about. And in fact, yesterday, we're gonna talk a little bit about how we might put this stuff to use. And so, there we go. All right, so our plan, our little path we're gonna take, we're gonna start with a little just sort of framework setting of what it is I think about when I talk about policy relevant. And then we're gonna have a little walk down memory lane, talk to you a little bit about some non-CO2 stuff that I had interaction with, and then get to that Paris Agreement global stocktake conversation. So again, this is maybe not in your technical land of expertise. I'll try to make a few tie-ins, but it's also just thinking about this in the big picture of the world. So policy relevance, what does that mean? When I think about what happens with the work that we do, we might be informing someone very directly. We might just be contributing to the bigger scientific conversation. We might have quantitative results that actually let someone evaluate the efficacy of something that they did. And it could be in the international realm. It could be in your local community. There's a lot of potential venues we're talking about. So it's a mushy word, policy relevant. I'm not really talking about going to court in a legal battle over something. It's much more in like an ecosystem of work that maybe is pushing the policy along, informing a conversation, that sort of world of policy relevance. And I'll show you more specifics as we go. So when I was a graduate student back in the day, my office mate, Rob Harley, was working on analysis for Los Angeles. And the problem that he set out to solve was if I measure the composition of the atmospheric materials, and in particular looking for organic carbons, he has some idea what he finds. And then there was an estimate that the state had made about what they thought was being emitted, in particular from vehicles. And what he saw was if you took the inventory and compared it to the observations, there was a big mismatch in things like N-hexane, toluene, and alkanes. They were really different from what you might expect from the inventory. So then he went in and tried to figure out, well, what could be the explanation for that? And his conclusion was basically that vehicles aren't burning the fuel that efficiently, and there's a lot of unburned gasoline that's getting out in the atmosphere, and that could account for the difference between the inventory and what they saw. And so this actually was a piece of information that the state of California used as they were evolving their regulations. And if you think back to cars and how have evolved, there's a couple of things in specific that this was involved in helping us change. And one of those was, it used to be that you put the nozzle of the gas pump in your car and there was just free air around that, but now there's actually vapor recovery systems on a lot of those. And that was trying to like get back some of this venting that was happening. And then also just the way your cars are built and the gas vapors get vented was a factor, as well as things like cold starts and what the engines work like when they just get started up. So this was a way that our science was actually being used by the state of California in their conversations about how they might change what they do and try to get the vehicle emissions reduced. And one of my projects was, when I did this, I was like, oh man, we're state of the art. This is so exciting. We were thinking about visibility in Pasadena. And two things you should know. I arrived there as a graduate student in 1984. And I don't know who's been to Pasadena. Okay, Deborah for sure. Or looked at pictures. There's beautiful mountains that are the backdrop of the city. When I arrived in September 1988, it took a few months till I knew there were beautiful mountains as a backdrop to the city, because there was so much smog. The visibility was incredibly bad. You didn't see them for months at a time. And we did this project. I was working with people at JPL. We were using image processing software, which now looks like the hokiest thing in the world, because we didn't have digital cameras. We took film images and then we scanned them in and read the film density to get information about that image and then manipulate it in software. And what we were trying to do was find a way to communicate visibility information as well as connect aerosol properties to the visibility. And we knew that if I told you the light extinction was 10 to the minus 4 kilometers, it didn't mean anything to you, but a picture might help. So this was an experiment where they waited till, get the name, they had the event of the heavy winds that basically bring the air outside of the city. Santa Ana, thank you. So this was photos taken on a Santa Ana day. This is one of the roofs of a famous building on the Caltech campus. And you can see these mountains, I think about 10 kilometers away to the ridge line here. So this was a clear day. These are photographs that were taken on a typical day, smoggy, maybe a little extra smoggy, but still fairly typical in August. And then we had measurements of those aerosols and calculated the light scattering and used the image processing to insert smog. And so if you insert smog numerically into this clear day, you could produce this. And it represented a lot of the features of what we had seen in those photographs. So just finding out, can I understand the light scattering and then actually use it in a numerical way so it's a tool for showing what aerosol effects are going to be. And then the student who followed after me did more analysis where he said, well, let's say we have different ideas about how to clean up the air in LA. If we had a magic wand, we could get rid of the primary particles. So like the small particles that flow into the city, a different magic wand, we might get rid of all the sulfate. And in reality, it's going to be some sort of a balance. So he calculated what he thought the volume distribution of the particles would be and where it was coming from. We have things like sea salt, engines, road dust, etc. So he came up with all these profiles using a microphysics calculation and then calculated the light scattering coefficients. And again, his table of what the coefficients are doesn't help you that much. He did at least transform that into a visibility range. So in the baseline, you can only see 10 kilometers. If you really clean it up, you'll see 20. And then we used what we thought were super cool new tools and took satellite images and tried to put ourselves on the ground and rotate it. The kind of thing you do in Google Earth now where you just like drop yourself in a pin. We were like, and then the base case and then these different cleanups. So we were trying to make our information useful, feed it into the state and the local air quality management district, find a way to communicate more effectively instead of just a number, but with an image about visibility and what air quality control measures might do to the visibility. And of course, I was in LA at the perfect time to do these experiments. The Caltech students can't do this anymore because you see the mountains pretty much every day. They clean it all up. All the fun is gone. But there's other places we can go and do the work. So that's what I did in my graduate days. And then it was really neat to see as things evolve. This was a paper from 2006, and there were satellite measurements now being made of nitrogen dioxide. And they asked themselves, can I explain what I see with the observations based on what our agencies are saying they think the emissions are? And so this upper figure is from the Skiamaki, it's a European satellite showing the NO2. And the NO2 is a good molecule to focus on. It has a pretty short lifetime, so you kind of see it where it's emitted and it decays away. So you can see hotspots happening here. And then with the baseline emissions, you see a very different picture. It looks like there should be a ton more than there was. But this data was collected at a time when the US regulations were evolving pretty rapidly and the change was happening on the ground. And so these were a way to really start convincing people that actually some of this data might help you find out, did that change program happen? Is it as effective as I thought it is? Is there some emission spot I'm missing? So this, this wasn't at the end of the story, but it was one of the earlier papers I remember and thinking, wow, we really can do some useful stuff with these satellite measurements. And of course, there's a lot of details of like, where was that NO2? Was it near the surface? Was it in the upper atmosphere? How many days did they aggregate? And was the weighting really right? Like, it's not perfect, but it's a field that's evolving and was a nice demonstration in the early days. So these are all not carbon dioxide, but they were things I had my connection with. And when I think about the Paris Agreement and our carbon dioxide challenges, I like to remind myself we have had success in the world as international collaborators in addressing some of our big issues. The Montreal Protocol is one of these examples. Certainly there's aspects of it that made it was simpler to solve than what we're trying to do these days, but it is a nice example. So the Montreal Protocol is the agreement that was made internationally to reduce the emissions and eventually end emissions of ozone depleting substances. And one of the things that I really find interesting about this is there's people that I've met in my work that were actually part of the teams that were going and measuring ozone at the poles and finding this hole in the ozone, and then working on figuring out what is going on, what's the chemistry behind this, what are the drivers. And this was an amazing time where there was scientific expertise, international policy, and industry that actually were talking together, working together, informing one another, and that allowed them to come to agreement that in fact, these gases were the critical catalyst to reduce the ozone destruction in the stratosphere, and they would start making changes and reduce the production of them. So you see between 86 and to the 2000, incredible reduction, particularly in CFCs, HCFCs, and carbon tetrachloride. The story's not over here with the Montreal Protocol, and I'll touch on that in a couple of slides, but it is an example where in an international problem, scientific expertise, policymaker industries worked together, got new understanding, made an agreement and acted on it and made change that's had a positive effect. So we've seen it happen before. It's harder to make it happen right now, but there is examples of where this has occurred. All right, so now we're going to get into the Paris Agreement, and I apologize. There's going to be a few word slides here as I just try to get a few concepts out, but you don't feel like you have to read it. That's for future reference. So in lead up to the Paris Agreement, Earth Summit happened in '92, and that's where a lot of the countries of the world said, yeah, we should join together in this UN Framework Convention for Climate Change. So '92 is sort of the date that had happened. And just so you don't get confused, in fact, what we did with OCO2 wasn't really driven by that. We were doing proposals in that same time period, but it was much more like what's going on in the science, what's the overall climate or overall carbon cycle. It wasn't like we said, oh, there's going to be this climate change convention and we're going to make data that matches to it. It was sort of independent things happening at the same time. So the '92 date is important. And then in 1997, the Kyoto Protocol was adopted. And I'll show you a little few details in a moment. What was also notable in the bad side on Kyoto protocols, the US and China did not agree to that. And we are big players in the room on the greenhouse gas emission world. But then in 2015, we had the Paris Agreement. So I'm going to tell you a little bit about these different agreements and sort of what they were idea-wise, what they were in like actual hard commitment, and then what some of the needs they created and how our communities get involved in that. So the Kyoto was a first important step. And one thing I want to note here is we'll talk a lot about CO2, but of course, if you're going to address climate change, it's all the climate gases that are in this Kyoto protocol, the SF6, CFCs, N2O, et cetera. And in this agreement, all the countries that were Annex 1, so the more developed countries, agreed to mandatory emission reducing targets, and the amount that they agreed upon was different for each country. So this was a big step forward. We had actual agreement, numbers were talked about, all the gases were identified. And this first commitment period started in 2008 and ended in 2012. And what we saw as a impact of this is countries did reduce emissions, but you had Annex 1 countries reducing. And right when Canada decides it want to take action, it probably really does take action and things happen. But when you make that pie chart of the whole world, it's just a little sliver. So we've actually seen Europe is really make commitment and changing things, but they're such a small player, it's not like shifting the whole story. It's really US, China, India, that are the huge players. So those developed countries reduced their emissions, but overall emissions increased in that 1990 to 2010 period because of all the other countries that were continuing. So in 2012, there was another step forward where they said we better extend that Kyoto protocol. It had reached its endpoint, but they wanted to increase it. 37 countries with binding targets and a lot more people signing on and saying, yeah, we think this is important and we're going to do something about it. So it's still a target, an agreement, but there's a little more participation developing. And in that meeting, that Doha meeting, you sort of got this reaffirmation that we've actually got to buckle down people and get serious. So what they said was by 2015, we'll have a climate treaty and that will actually have requirements. So they said, we're not going to build the teeth right now, but we'll commit that by 2015, that's going to happen. And these, you probably hear about the COP meetings, maybe you're quite familiar, but these are the Conference of Party meetings where this stuff happens every year. So the COP meetings are the forum where agreements get happen, although of course there's work going on all year and conversations and technical work, et cetera, et cetera. So Doha, they reaffirmed their pledge. And then in 2015 was when this new agreement, the Paris Agreement, was actually adopted. It replaces the Kyoto Protocol, and it's where all the countries actually sign on and make commitments. And I'll show that a little bit of what those commitments are like in a second. So now you've got 195 countries engaged in this process. So you're really starting to get more international participation. And yes, I come from a country that's been a little bit of a flip-flopper here, you know, because when we say the Paris Agreement was signed, who am I talking about? Well, it's the Department of State in the US, our diplomatic agency, that's signing that agreement. It's not the EPA, it's not the science community, it's done through our Department of State. And so you have presidents changing, prime ministers, et cetera, et cetera. So unfortunately, you know, we signed on to the Paris Agreement, but then our president changed and the Trump administration didn't want to be involved in that. So they said, no, we're going to get out. They couldn't get out immediately because there was this agreement. It had to be 3 years after the initial signing. But then he did withdraw on the 4th of November, shortly before the election. And then Biden won that election. And once he was inaugurated, he next day signed us back into the Paris Agreement. And this, I think, is just, it's ridiculous and it's a mess. Like, you really want countries committed and working and not like flipping and flopping around with the politicians. But, you know, these are international agreements. They're not a science agreement. So you have a lot of players in the room. And how does this actually practically work? So countries had to make what they call the nationally determined contributions, and that's where they tally up what it is they're emitting for greenhouse gases among all those gases we talked about. So the countries have their nationally determined contributions, and then the Paris Agreement says, okay, you need to reduce them every 5 years. And it doesn't give an amount, there's no like schedule of reduction, but it says you should increase your ambition and reduce your contributions. And then to help that process along is something called a global stock take. So where we try to make some assessment of what do we see is actually happening with these emissions. Are we meeting our nationally determined contributions? And then the idea that it's kind of peer pressure and community pressure to get everybody to reduce their contributions bit by bit. And there are many tools and techniques for inventories that help feed into these NDCs. So I'll take just a minute to talk a little bit about that and the global stock take in a little more like technical detail. So a lot of the inventories that get used in these kind of activities are what we call bottom up. And that means, for example, if you want to know about emissions from vehicles, you get some idea of vehicle counts and miles traveled and efficiency of burning the fuel, and you calculate all that into some estimate of the emissions. And there's techniques and emission factors for a lot of different things: agriculture, industry, transportation, fuel for heating, et cetera, et cetera. So you find out how much are people doing of these activities, how much do you typically emit per activity, and multiply it up to get an emissions estimate. So this is, a pretty standard type of thing. And the UN has protocols that people can use in doing this. There's companies that'll sell services, spreadsheets you can grab. So that's like a kind of a very typical approach. And then, of course, those of us who do atmospheric observations are like, hey, I see stuff, I can help out with this. So another label we use is atmospheric-based approaches. But it's not like you don't need an emissions inventory to do this. You start with some sort of emission estimate from activity-based approach. You add in some information from your observations. You try to do an inversion and then come back with an update and say, does this emission estimate seem to be consistent with my observations? And there's a lot of details and variations in how people do this. You might make an emission estimate at a country scale. You might do it on anyone heard of Transcom regions, kind of big blocky regions we break the world up into back when the computers were slow. You might do it for one state and try to do an emission inventory assessment there. So this is just a super high level of what is a big field of work for atmospheric-based approaches. And then there are folks who are trying to even innovate on that. So we could have emissions estimates, atmospheric observations, and then also what we call non-traditional data. Like people take night lights as some way they might infer something about activity in an area. You might grab traffic data from Google and feed that into your model. People try to use thermal infrared as a way of finding concrete production numbers. There's just all sorts of innovations that people are using to try to bring new information into the conversation. So this is a rapidly evolving field about how do I understand what the emissions were from different sources and from different regions. So, and generally just a couple comments, usually this is pretty iterative. You don't just make one and leave it because activities are changing or you have some new insights. So it's always an iterative process. As people try to drive down to like city scale or smaller spatial scale, or say monthly data instead of annual data, your uncertainty tends to grow. And of course, I'm going to show you a little example with the CFCs, where you've got limited sources and no or limited removal processes. It all works a lot better than if you're like talking about methane, where you've got cows and wetlands and industry, time dependence, et cetera. So it becomes a much more complicated problem to try to connect the pieces. And so CFCs is just another great example, kind of tying to that Montreal Protocol. And I think you actually had Steve Monska come and talk to the department a couple of years ago. But this is where NOAA in the US is part of the network that's making measurements and continually monitoring what the CFC concentrations are. And then because of Montreal Protocol, we expect them to follow this sort of decline. So everybody is like, what's going on? Because the red and black lines are indicative of what it was they were actually seeing. So back in 2018, they started to see data that suggested the decline was not along the trajectory expected. And so they shared that information, there were conversations. And so you also see that unexpected increase and then things seem to go back down. And in a paper that was a companion of that, they actually did analysis with 2 measurement sites here and tried to figure out where are the emissions coming from. And in their analysis, they locate those emissions in China. And again, you saw these increase, and then the estimate is that the emissions decrease. So it appears to those of us on the outside that they discovered this with their observations, but then there was a little conversation in the back channels, and then activity declined and was stopped in China with the production of the CFCs. So it's a really interesting story about how our observations feed into the conversation, and we see now a response to that. So CO2 is not as nice as CFCs, a lot more complication, but we're still going to try to make progress on this problem. So the global stocktake, this is a figure I stole from the World Resources Institute, one of the nonprofits that works in this arena, and they kind of break it down into the steps that happen. So here countries are building reports, findings about their emissions, then they write a synthesis report on this. It goes to some technical assessment, series of in-person dialogues, and then consideration of the outputs where the countries discuss their findings. And then the nations use those findings to step up their plans and add ambition. And I had the opportunity to actually go to the COP27 meeting in Egypt last year and do some presentations about how remote sensing data might contribute to it. And it was a really, really interesting experience because you have these arenas and hallways where scientists and technical people are talking. Many countries have booths, and we actually did a presentation at the Japan booth because Japan's very involved in trying to advance remote sensing information. And then you could walk back to where the delegates are, and there's actually these rooms with just all these folks, generally in suits, where they're having these discussions about the findings and the background. I mean, you can already see that this language in these flow it's different than the language I use in my everyday work, right? I don't talk about consolidation and climate finance issues. We're going to review this information. We're going to step up our national climate action. So it's wrapped in sort of a political dialogue on top of the technical dialogue. And if you go to the website of the UNFCCC and try to look at the global stocktake, it's not a bunch of pie charts and graphs. It's, you know, documents that are submitted by different institutions and countries. So, you know, you have the national communication. This is where you actually see the record of what their ambition or their national contributions were. But you have things like best practice in aligning international public financing with the Paris Agreement, or another one I found in here was sort of on, where'd you go? Implications of climate policy on energy poverty. So there's many layers that come in, and the UN Sustainable Goals are really at the forefront of people's thinking. So it's conversations about, you know, what's the societal impacts of change? Who's going to pay for this to happen? What's the equitable solution? What's the technical barrier to me doing it? So a lot of different threads that are being discussed. And this is a picture of, you know, the real technical work that ends up feeding into, did we meet our commitment? Did we not? What are we going to plan to do next? So my science work is important, but it's just this little cog in a bigger machine that is the world's arena for discussing how we're responding to climate change. right? So I'm always excited about my OCO observations. I love doing remote sensing. So how do I connect the dots here from remote sensing data to that strange conversation in the framework? And this is one of the ways that I've seen the community try to make a contribution lately. So there was a paper that I'll talk about a little bit from the collaboration of folks who work with the OCO2 data and their data assimilation models. You see here the large set of authors. This was driven by Brendan Byrne, who I think is a graduate of the department, right? And you'll see many familiar faces here. So they wrote a paper with the global stocktake schedule in mind, saying, let's try to prepare something that can be part of this conversation. And I think, Brendan was really committed to doing this. He probably had some collaborators who were enthusiastic, some maybe dragging their feet. And I think some of the concern is he wrote this paper. I'll show you some of the figures and key findings. But this stuff gets in the hand of our public affairs office, and you end up with a website that says something like this: NASA is taking stock of carbon dioxide emissions by country. And I can't tell you how many headlines I've seen from the work we do where they're like spy in the sky or eyes on the earth, or, the twist that people use when they talk about it in some of the news arenas makes us nervous. So I think we have to find some sort of a balance between like, this might be taken incorrectly versus I have insights and information. I have to try to insert that in the conversation somehow. So what did Brendan and team do with this stock take effort that they had? So there was an activity. Did I forget to write that down? Let me see. Hold on. Yeah, okay. So there's the OCO2 community had done a model intercomparison project. Some of you probably worked on MIPS. So there's a MIP that they did with many different groups participating to run their models and make estimates of the carbon fluxes. And that was the basic set of data that Brendan used in this analysis. But what I want to highlight is that in this figure, the things that are italicized and bolded are what he's estimating from the model, whereas other things are bottom-up estimates. So the fossil fuel emission is set. That's a bottoms-up estimate that's inside the model. The lateral flows of carbon are a bottom-up estimate. It's only this biosphere exchange, net biosphere exchange, that he can actually estimate in the model setup. And so that's what they did in this work, and then reported it in the typical 1 degree by 1 degree grid, as well as try to put it on a country basis, because that's what the framework of the global stocktake is. And some of the comments he makes in that paper is that, it's hard to differentiate land, unmanaged and managed lands. The fossil fuel CO2 errors themselves may have, fossil fuel emissions may have some errors. And then the part that is difficult for some of us to accept is we still see that if you take the land measurements of OCO and do this problem, if you take the over the ocean measurements of OCO and do this problem, they are not in complete agreement. So the satellite data feeds in, but even within the data we provide, there's some discrepancies. And then of course, modelers know transport errors are another issue we have in any of the global modeling exercises. So there's plenty of ways where the uncertainty feeds in. And so I think it's, in my mind, the group made a good decision to try to get engaged in the conversation. It's also important to try to present this in the right way, where, Brendan wrote in his paper, for future stock takes, these kind of estimates will get revised. Information will expand for observations, algorithms will improve. So I think he's trying to say, like, this is not the end all and be all, but here's a way we're going to try to contribute what we know and add some new information to the process. And one other comment I wanted to make on this, one other concern that some of us have is if we are effective in getting our fossil fuel emissions down, the agriculture, forest, lands, those have become a larger and larger term in this whole problem. So right now, it's not something that's working perfectly, but it's going to become like the big player in the room in another decade or two. So where do we go from here? Well, I mean, the CO2M folks in a way are kind of trying to build something that's going to really complement the kind of work you saw in Brendan's paper. because I mentioned in one of the earlier talks, they're really focused on the anthropogenic CO2 emissions. So where Brendan is showing that he's got to use a bottom-up estimate, these guys are trying to figure out how do they provide some observational data that feeds into this. And we talked about this the other day, how they measure carbon dioxide as well as NO2, which will help them really get to where some of the emission points are. But what's also interesting, if you look at this, that BAMS article again, is they try to really fill out the framework of what they're doing. And they talk about trying to provide services. They talk about monitoring and verification are the words they use. In my experience in the US, there's huge hesitation to use those words because of the implications, but the Europeans are ready to go ahead and do it. And they show like we have this satellite data in the context of in situ and other information feeding into our assimilation system that's also got emissions and priors. And they want to try to get out country fossil fuel emissions, city fossil fuel emissions, and hotspots. So that's their goal, to feed it into decision support. So they have this framework. And what I think is actually encouraging about what they're doing is they lay out this framework, but they also lay out a plan to get to it, where they're going to have funding and activities that helps build the block. So you see, starting in 2015 and running all the way to 2030, this is how they imagine the pieces all fit together. So they're developing their mission design concepts and what they call the space ground segment. So that's the folks who are going to get the data and process it and make the CO2. They're developing the Sentinel constellation, and they're developing R&D activities, which I'll speak about in a moment. So they do have this multi-pronged framework and funded activities to try to drive themselves to this operational stage. So the global stocktake already happened, and then they're saying, well, we want to be ready and in action so we can contribute to the second global stocktake in our work. So it's, to me, impressive that it is a comprehensive view of what's needed. It's not just like, oh, I'll build a satellite and then someone else will figure out what to do with the data. They're trying to put the pieces together, and they have some realistic thinking. This is one of the figures I pulled from that BAMS paper where they show, Europe with some estimate of the emissions shown with the colors, and really just saying, obviously it's challenging to monitor and verify a country's annual inventory based on atmospheric observations over time. You have small countries, one next to the other with very different kinds of activities and level of activities, and pulling that apart is not going to be straightforward. So they admit that, but they're still trying to drive down the road and get there. And these are just some snapshots from the different funded activities. And this is where I see the community I work with intersecting with that grand vision. So Verify was a funded activity. One of the highlights they say is we're reconciling state reporting and scientific climate data. So trying to, again, do this comparison of emission estimates and what they see in the observations. And they, talk about how their work fits in with the COP activities. So we see the science community engaging and trying to write papers and even some summary documents they can give to policymakers about what they're finding. And in specific, there's papers that have country inventories done with different ways. They've shown they have more success with the CFCs than they do with the CO2, but they're working their way through the problem. They had another big activity coordinated by the ECMWF on CO2 human emissions, or CHE. So this was a 3-year activity where they got scientists together to try to work on this problem. That wrapped up, and now their big thing is the Copernicus CO2 service. So there's funding efforts, big consortium working on this to try to prepare themselves to get these capacities ready and really bring that data to the policy world. So this is the biggest activity I know of where there's really coordinated effort to try to get science work, new instrumentation, get the tool sets built so we can feed it in to policy discussions in the CO2 realm. And then, of course, that's not the only game in town. You have activity happening all over the place. And these are just a few snapshots of things. Of course, California in the US is often been at the cutting edge of developing environmental policy, trying to put new restrictions in place, get on electric cars, clean up the air quality, deal with the methane. EPA is actually our regulatory body, so we see work in the US where there's regulation about vehicles. This was interesting. The city of Ithaca, New York is trying to go all electric. And so I've heard some podcasts where they talk about their efforts to like get people using heat pumps and conduction stoves, and what are they going to do about the vehicles? What are the practical barriers they follow? So, you know, activity happening all over the place. Tokyo's got their own plan to try to get to zero emissions. Corporate world, right? How many things do you pick up or see ads and it's like, you know, we're trying to get to net zero. We're going to start producing this stuff. It's going to be net zero. You can buy carbon credits on your aircraft. Unclear like how much of that is reality and how much of that is hype, but there's conversations happening in places that they weren't happening a while ago. Right? This is when I pulled out. AT&T says they're going to be carbon neutral by 2035. I don't know exactly how they're going to do that. How are they going to verify they did that? How are we going to write it in their report, or somebody on the outside? Am I going to start a consulting company and go sell services to like verify things for people? It's a little bit Wild West out there right now, but things are happening. So that's I guess it's good things are happening. And so back to, you know, some practical actual things. So the state of California is definitely an actor. And then methane is that other topic I spent a bunch of time talking about this week. And this is just an example of analysis that had been done. I think this is the Fisher paper where they tried to look at the state of California, and in this case, use some ground-based measurements to try to assess whether the inventory was consistent with the observations for California. And so basically they see their posterior, or the observation-driven estimates tend to be higher than the bottom-up estimates for methane. And then they tried to look at what particular sectors were probably contributing to that. So the state of California is engaged in these activities that try to make assessments of their inventories. And then one of the other areas in methane is now on the US level. So folks are using satellite data to try to make estimates of the methane emissions over the US, and then talk with the EPA to try to get updates to the inventory. So we're seeing that iterative cycle happening. Methane is where there's a bit more action right now, I think, just because of the data availability, maybe more uncertainty in the inventory, and then this new conversation that's happening. And then of course, these plume finders that I talk about and the aircraft that are a warm-up exercise are trying to work with producers and identify, you know, wells, pipelines, livestock, coal vent, and just find this stuff. And in many cases, this was an example that JPL has where they found a landfill, had all sorts of leaky methane, went and talked to the folks. They did a revision to the landfill, and then they went back and saw that that methane had been reduced. You know, so creating data that's policy relevant, again, it could be working with the landfill operator, working with the state of California, working in the context of this global effort to try to reduce emissions through the Paris Agreement. So a lot of places we might be able to insert and contribute ourselves. So just kind of a closing thoughts, it's like, what's our role in trying to help policy with the science we do? There's a lot of venues and a lot of scales. Montreal Protocol was a great example of where the scientists were really, they're in the room with their information in the discussions about what's going on there. For the global stocktake, it's a different arena. COP27 is the venue. We don't really talk to decision makers, but we go in and we try to present stuff. I've got a friend who's like a CFC expert, so she gets 2 steps closer to the big guys. I did see John Kerry walking across the venue. Didn't get to talk to him, but I saw him there. So it's a different world, but I do feel like the kind of information we have and the activities we do, they're important, right? They're important observations. They're going to become more and more important as we try to make change, and we've got to figure out if it's actually happening, or there was something in the system we weren't thinking about that's actually responding. So I think the work we do is really important. It's, you know, different parts of the world are doing it in different ways. The European have a huge coalition structure, plan, funded activity. In the US, we tend to be a little bit more on your own doing the work. But I think with activities on different fronts and different styles, it'll probably get us moving along. And even the kind of things some of the folks are doing with CMIP reports and the IPCC, that stuff's all important in pushing along the conversation and helping us identify where the areas are that change is needed, or the areas that are most vulnerable. When we think, where is rapid climate change going to happen? What's going to be the societal impacts? Who's most vulnerable? I feel like that's really important info, and the kind of things we do feed into it. So hopefully I've convinced you. You may not feel like you're a policymaker, but ultimately a lot of the work that we're doing in our science community feeds in either indirectly or a little bit more directly. And for me, it's important to feel like what I'm doing is kind of contributing in some positive way. And, you know, even sometimes I stop and I think, it's like, is this stuff worth doing? Why am I sweating so hard? But you know, I can do that, but it's really fun. Also, sometimes I'll go and talk to school kids and see like what they're excited about. And do you know these words? Community level engagement for me can be rewarding because you're much more directly involved in it. And there's all sorts of opportunities. AGU is one of our big professional groups, and they have a thriving Earth Action network where communities will come to the AGU and say, hey, I need some expertise and knowledge. And they provide opportunities for you to connect and go work with people. So there's definitely, all sorts of opportunities to get out there and do something. And my little blue swirly is just that. It's not like, I remember having one of these setups where you could lift a ball up on one end and there's a few of them on a string and they go click, 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 and kind of directly feeding back. It's not that kind of a process. It's a little more of a pushing on a wet noodle process, but over time we see that things do change. So I'm just going to wrap up and say it's been a super, super fun week. I know it's not over yet, but some of you I might not see, but it's been a really, really fun week for me. And hopefully I did convince you that satellites are a powerful tool, particularly the area of CO2 and methane. CO2 has been quite a trip since we put OCO up in space and tried to convince the naysayers that we have informative measurements. They haven't solved all of the problems, but we're advancing. And methane's a whole new arena and a lot of fun stuff happening. And for sure, there's still work to do, whether it be in the inversion models or how we connect this data to standards, how we're going to make all of the data sets useful together. So the challenges aren't over, and there's deep technical work that needs to be done. But I also do feel like our efforts are part of the ecosystem that's informing these international efforts. And so for me, that motivates me to keep involved and try to address what I think is, it's really the greatest challenge of our lifetimes, especially for those of you who are a bit younger than me. I mean, the way things are unfolding, climate change is probably going to dominate the conversation about a lot of decisions across the globe for your lifetime. So for me, it feels good to be involved in science work that's in that arena and having some positive change. And appreciate you listening to me all week as I tried to tell my story and spin it in the way that I understand it. So thank you again.